After velocity, we come to acceleration field. And in the acceleration field, as you know, that velocity is x by t or dx by dt, the distance traveled divided by the time. And so, and acceleration therefore is, if I have to represent, some people, we represent it here by the vector a, and this will be by v over t. So the rate of change of velocity with respect to time is acceleration. And again, acceleration field plays a very important role in the, not only in solid mechanics, but also in study of fluid flow mechanics. So therefore, and then the basis of all these things come into play, and they are Newton's laws of motion. And as you know, Newton's second law of motion, F is equal to ma, sometimes we represent, where F is the applied force, m is the mass, and a is the acceleration. This study of these things is so important that we need to consider that, we need to define it in all our equations that will be developed later on, that we will be studying, solving. These parameters play important role. So let's just see, as shown in the picture, if we look at a particle at time t, we want to know where it goes at t plus dt after a small time. Whenever in calculus, we always make a small difference and then we consider the whole setup. We generalize that in the region that is under consideration. The same here. So the x component of the particle, the y component of the particle, the z component of the particle. So that means here we are considering each particle that is under consideration and its movement and its velocity, change in velocity after a certain time. So this one, as you are familiar by now, is known as Lagrangian method, following each particle, keeping track of that, and therefore at times it becomes difficult to follow it. Acceleration for the particle, when we will be writing that, is therefore written as a particle equal to derivative of velocity of that particle with respect to time. Remember, each particle is being followed. Therefore, in our equations also, we are writing here the particle as a suffix. In Euler system, we will drop it. It will not be very necessary. So the same picture here, the Newton's law, second law of motion is shown, and you can see that acceleration is very important, because when a force is applied on the fluid, then it is governed by the law force is equal to mass into acceleration. Of course, the further elaboration of acceleration, its calculation, computation, variation differs from or depending upon the situation of the flow. If we have to write the velocity field and the acceleration fields in our vector notation for an individual particles, then we will be writing it as this. And the only, well, you are very familiar with all these things, so I will be rushing through them rather quickly. But the only thing here to note is that acceleration that is defined as dv by dt is, when we differentiate it, then d partial derivative of v with respect to time into dt by dt, and plus there are three more terms as well. Partial derivative of each term. So dv by dx and dx by dt, we are familiar, we denote it by u in the x direction. So we may write it as u particle. Similarly, this will be v, and this will be maybe the w component or the z component. And you can see that this is summarized here in this form. It's important that we compute these, whether they become zero or non-zero, but we need to make the complete calculation. And as we define in our vector notations, the del is denoted by partial derivative of x, I into partial derivative of x plus j into partial derivative with respect to y plus k into partial derivative of z in the z direction. As a whole, this is called as sometimes gradient, sometimes del. The difference is del is a vector. It's taken to be a vector quantity. It's known to be a vector quantity. Therefore, you can see an arrowhead there. And this can be applied. Del can be applied to any other quantity as a whole. So, let's say if there is a function f, we can apply this del on f, and so on. So its partial derivative in the three directions will be taken. The first component, this one, partial derivative of v with respect to time, is known as local acceleration. dv by dt is acceleration as well as a whole, but the partial derivative of v with respect to time will be defined as local acceleration. And then all the other terms are known as advective or convective acceleration, and they are non-zero for steady motion or steady motion. Both of them, they can be non-zero depending upon how the values are, how the fluid is moving. So separately, if I want to write down the acceleration field, ax will be written as this, ay and az as shown. And the three components are known as advective acceleration, while these terms is known as local acceleration.